So the final energy minus initial energy will give you delta E. N square we know the energy level which is corresponding to the electron, and then Z is the atomic number. So in case of absorption spectrum, NF value will be greater than Ni. Zeeman effect is the splitting of spectral lines in the presence of magnetic field. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. So today we are here with the session 5 of the chapter Structure of Atom. Yes, so in last class we discussed about atomic spectra, line spectra, and especially line spectrum of hydrogen, and then the postulates of Bohr's model of atom. So in today's session, we will be discussing about the Bohr's theory for hydrogen atom. Yes, and the line spectrum of hydrogen, how you will be able to explain line spectrum of hydrogen using Bohr's theory for hydrogen atom. Yes, and finally towards quantum mechanical model of atom, which were the developments leading to the quantum mechanical model of atom, we will be discussing in this session. So, beginning with Bohr's theory of hydrogen atom. Let's see. The stationary states for electron are numbered as n is equal to 1, 2, 3. These integral numbers are known as principal quantum numbers. So, in last session, we discussed about this. Yes, there will be various energy levels which are represented by this is n is equal to 3, this is n is equal to 2, this is n is equal to 1. Yes, basically this n is known as principal quantum number, which we will be studying in the upcoming sessions. Right. And the radii of the stationary states are expressed using the equation Rn is equal to n square into A naught. Yes, using Bohr's model of atom or Bohr's theory for hydrogen atom, we can calculate the radius of each of these stationary states. The radius corresponding to each of these energy levels can be calculated using the equation Rn equals Rn, that is which energy state it is, that corresponds to n, which will be equal to n square into A naught. The value for A naught is 52.9 picometer, and n will correspond to the shell or the principal quantum number. Yes, n is equal to 1, 2, 3. Which value it is, you have to substitute in here. So, let's see what will be the radius of the first energy level. So, let's say Rn, how we can write it? R1, right, will be equal to 1 square into A naught. 1 square is 1, A naught value is 52.9 picometer, right? So, this will be the radius of your first orbit or first energy level corresponding to n is equal to 1, right? So, this radius where n is equal to 1, the radius is called as Bohr radius. Clear? Where R is equal to 52.9 picometer, it is called as Bohr's radius. Clear? Now, the energy of stationary state is given by the expression. The radius we can calculate. Same way, there was an equation which was developed by Bohr to find out the energy of these stationary states. En is equal to minus RH into 1 by n square. So, RH is called as the Rydberg's constant, which is having a value of 2.18 into 10 to the power minus 18 joules. Yes, so that is about the energy corresponding to the different stationary states. Yes, so En is equal to minus RH into 1 by n square. So, n will correspond to which energy level the electron is present in. Yes. Now, for hydrogen atom, we saw the equation is as this. En is equal to minus RH into 1 by n square. Clear? Now, for hydrogen-like species also, Bohr was able to formulate an equation. That is, En is equal to minus 2.18 into 10 to the power minus 18. That is basically RH, right? Yes. Minus RH into Z square by n square. So, what was the equation here? It was just 1 by n square. A Z square was also introduced. So, what is Z? Z is the atomic number of your particular atom. For hydrogen-like species, you can use this equation. So, what is hydrogen-like species? Let us consider helium. Okay, helium consists of 2 electrons. Now, what about helium plus ion? Yes, 1 electron is lost. Now it behaves, or it will be like hydrogen atom, right? Only one electron. So that is what is written here for hydrogen-like species. Helium plus can be an example for it. Lithium 2 plus can be an example for it. So I hope it is clear. So if it is in the case of helium plus that you have to find out the energy, it will be minus 2.18 into 10 to the power minus 18 into z square. In place of z, you have to substitute 2, right? Yes. So it will be 2 square by n square. Yes, clear. Now, radius also for a hydrogen-like species can be calculated using the equation 52.9 n square by z. Yes, n square we know the energy level which is corresponding to the electron, and then z is the atomic number. So, clear? These two equations are very important. Clear? Now we are going to find out how the line spectrum of hydrogen can be explained by the Bohr's model of atom or Bohr's theory. So let's say the energy gap between two orbitals is given by, from one orbital to another orbital, electron will keep jumping, right? So we know that there will be a difference in energy. So that energy difference is given by E final minus E initial. F corresponds to final and I is initial. Yes, so the final energy minus initial energy will give you delta E. Delta E is equal to minus RH by NF square minus of RH by NI square. So we studied that the energy corresponding to the stationary orbits or stationary states is minus RH into 1 by N square. So that is being used here. Delta E is equal to the energy corresponding to the final energy level minus energy of the initial state. Clear? So minus RH by NF square, the final energy, minus of RH by NI square. Clear? Now here minus and minus will become plus. Clear? So when you rearrange this, the final equation will be delta E is equal to, so from both of this RH can be taken outside, right? So what will be my equation? Delta E will be equal to RH into 1 by N I square minus 1 by NF square. Clear? Yes, RH can be taken outside. So that will be equal to 2.18 into 10 to the power minus 18, that is the RH value, into 1 by Ni square minus 1 by NF square. So I hope this is clear. Now, the frequency associated with absorption and emission of the photon can be equated as, we even studied how you can calculate the equation, right? For frequency, nu is equal to delta E by H, right? So, from here we obtain the delta E value, that is 2.18 into 10 to the power minus 18 into 1 by Ni square minus NF square, that you can use here. So, that will be RH by H, this H is written here, RH by H into 1 by Ni square minus 1 by NF square. So, the values are substituted here. We know H is the Planck's constant having a value 6.626 into 10 to the power minus 34, right? So, that is being substituted here into 1 by Ni square minus NF, 1 by NF square, which will give you the value as 3.39 into 10 to the power 15, 1 by Ni square minus 1 by NF square. So, I hope till here it is clear. Yes. So now we are going to see how you can represent it in terms of wave number. So nu bar will be equal to RH by HC. From where did this come? We know that nu bar is equal to 1 by lambda, right? We know that. And we also studied the equation, relation between velocity, frequency and wavelength. So that is C is equal to nu lambda. So if I am taking lambda to this side, I obtain 1 by lambda is equal to 1 by lambda will be equal to nu by C, right? So that is exactly what I have written here. Yes, that is nu bar will be equal to nu by C. What is nu? Nu is being calculated from here. That is RH by H into this value. Clear? Now to that one more C will be added. Clear? Nu bar is equal to nu by C. The nu value is RH by this much part is the nu value. Clear? And one C will be also there. Clear? Now calculating it with the values. What is the value for C? We know that C is 3 into 10 raised to 8 meter per second, right? So substituting all the values, finally we will obtain the nu bar, that is a wave number, as 1 0.09677 into 10 to the power 7 into 1 by Ni square minus 1 by Nf square. Yes, so have you seen this equation somewhere? Yes, this is the equation that we studied for the line spectrum of hydrogen, right? How to calculate the wavelength of the different series of the line spectrum of hydrogen, isn't it? Yes, so using Bohr's theory, we were able to explain the line spectrum of hydrogen. Clear? Yes. So in case of absorption spectrum, Nf value will be greater than Ni and the term is positive and energy is absorbed. So what you have to remember is, in case of absorption spectrum, if absorption is happening, Nf value will be greater than Ni. The final value will be greater than initial value and hence the term will be positive. Your energy will be positive. So what you can say, the final answer that you obtain will be positive. That means energy is being absorbed, you can conclude. Now, on the other hand, in case of emission spectrum, Ni will be greater than Nf and in that case the value will be negative. So what you can conclude, energy is being released. Yes, so till here I hope it is clear. So now let's do a numerical based on this equation that we have just studied. Calculate the energy associated with the first orbit of helium plus ion and what is the radius of this orbit. So what is this helium plus ion? It is hydrogen-like species, right? So we studied how we can calculate the energy for hydrogen-like species. It is En will be equal to minus RH into Z square by N square. Yes, Z square is introduced there because it is hydrogen-like species. So what it will be? Minus 2.18 into 10 to the power 18 into, what is the atomic number of helium? It is 2. It will be 2 square by 1 square, right? So that will be minus 2.18 into 10 to the power 18, 4 by 1. Clear? So the final answer will be minus 8.72 into 10 to the power 18 joules. So that will be the energy with the first orbit of helium plus. It is given first orbit of helium plus ion. That is why I took 1 square here, right? The N value is given as 1. Clear? Now also we have to find out the radius of this orbital. So what is the equation? Rn is equal to 52.9 into N square by Z, right? This was the equation we studied to find out the radius for hydrogen-like species. Clear? So that will be 52.9 into, what is your N? 1, right? 1 square by Z. The atomic number of helium is 2. So it is 52.9 divided by 2, which will give you 26.45 picometer. Clear? So we calculated the energy as well as the radius. So I hope it is clear. Now what you have to understand is that Bohr's model is also not the finally accepted model of atom. Even Bohr's model had its own limitations which led to the final model of atom we will be studying, that is quantum model of atom. Clear? So the limitations of your Bohr model of atom is couldn't explain atomic spectrum of multi-electron species. It was easily, using Bohr's theory, we were able to easily explain and understand. So the limitations of your Bohr model of atom is couldn't explain atomic spectrum of multi-electron species. It was easily, using Bohr's theory, we were able to easily explain and understand the line spectrum of hydrogen, right? Yes, but for multi-electron species or multi-electron atoms, the atomic spectra was not able to be explained using Bohr's model of atom. Now, failed to explain fine structure of spectral lines, could not give explanation for Zeeman effect and Stark effect. Now, what is Zeeman effect and Stark effect? Zeeman effect is the splitting of spectral lines in the presence of magnetic field. Okay, Zeeman effect. Okay, that is the splitting of spectral lines in presence of magnetic field. Clear? Yes. how in the presence of magnetic or electric field the spectral lines will act, he was not able to explain. So that is Zeeman effect, that is splitting of spectral lines in presence of magnetic field. And what is Stark effect? It is the splitting of spectral lines in the presence of electric field. Clear? So in the presence of magnetic and electric field, how the spectral lines would act, he was not able to explain. So these were the few limitations of the Bohr's model of atom, which led to the last one, that is quantum mechanical model of atom. So like we studied for Bohr's model of atom, which all are the developments which led to the Bohr's model of atom, same way we will be discussing it for quantum model of atom as well. So the first one is dual behavior of matter and the second one is Heisenberg's uncertainty principle. So in detail about these two we will be studying in the next session of your chapter. So in the next session we will be discussing on dual behavior of matter, Heisenberg's uncertainty principle, and finally the quantum mechanical model of atom. So I hope what and all we have discussed in this class is clear for you. Yes, so that's all for today. Thank you.